All right, question 4. This is about switching directions on mechanism. First case, I have no strong base, I have no strong nucleophile. That is purely SN1E1 condition. That's what this is. I have a tertiary carbon, I can't do anything 2-based. Substitute. I have a tertiary carbon, I can't do anything with strong reagents because I don't have any in this case. I just have a solvent. So, given that, the cation substitution's easier. It's an easier approach. Doesn't require removing another additional atom. But when I change to a strong nucleophile slash base, I get a completely different product distribution. I have not introduced SN2 here. A few people said that. No. There is no functional SN2 on a tertiary carbon. No. It's not approachable. The end. So this is still coming from SN1 somehow. That somehow not included in this is that the solvent is still ethanol. So we still have our SN1 nucleophile there. But the important part, the other piece, that is not an E1 now. We now have a strong base. E2 reaction, we're not worried about the carbon where the halogen is. We don't have to get to that. We're going next door to the adjacent carbon, which means the E2 reaction works just fine with a tertiary alkyl halide, as long as the hydrogens next door are accessible, and they are. In this case, they're all just methyl groups. So in this case, the change in direction is that we've introduced the E2 pathway, and that has taken over because we're using strong reagents instead of weak ones. Ethanol is not a strong base. It's not a strong nucleophile. It's a solvent, basically. Ethoxide is a strong nucleophile and a strong base. But only the strong base application here can really do anything. Now, technically though, the ethoxide could still act as an SN1 nucleophile. It's kind of pointless, but it's still going to hit a cation if one forms. So that is probably the likely origin of that 7%. The ethanol is still going to be much slower.